Alright, thermodynamics and kinetics of binding. In and outside the cell, molecules are encountering each other frequently. This is due to random thermal motion. If the encountering surfaces match each other, then binding can occur. The better the match, the greater the binding strength. The weaker the match, the weaker the binding strength. If the bound state is preferred, then binding is favorable. So what we're saying here is that if I had two molecules, A plus B, and they bind to each other, there's a bound state of A and B. Then if at equilibrium I have more of this than this, then this process of binding is favorable. So favorable if concentration of A and B bound to each other is greater than concentration of A plus concentration of B. I just have more in complex than I do alone together. Modeling the thermodynamics and kinetics of binding. Let's imagine two populations of molecules in an aqueous solution. One is protein A, and the second is the protein's ligand B. Through random thermal motion, these two molecules will collide with each other, and since they have complementary surfaces, will bind. After a short period of time, there will be three different populations in the solution. Protein A by itself, ligand B by itself, the protein-ligand complex. The process can be shown as such. A plus B goes to AB. The equilibrium constant for association is Ka equals to concentration of AB over concentration of A times concentration of B, where the delta G standard equals to negative RT natural log of Ka or negative 5.9 log of Ka, again in kilojoules per mole. So make sure we write that in. So the first question that can come up is, what about delta G? Now we're not really worried about delta G because in a binding reaction, so let's draw out our reaction and reaction progress. Well, if the process is favorable, meaning that it favors making the AB complex, then it will look like this. I start out with A plus B over here and AB down here. Now, there is no transition state for a binding reaction. There is no energy of activation bump to go through, so the reaction will simply go downhill, right? So it will quickly reach the equilibrium state. And if it reaches the equilibrium state, delta G equals to 0. So if delta G equals to 0, our previous equation that we had was delta G equals to delta G standard plus 5.9 log of concentration of the product side, which in this case would be concentration of AB, over the concentrations of the reactants, or the initial state, times each other. So this would be concentration of A times concentration of B. Right? So delta G equals to 0. Boom. Delta G standard plus 5.9 log of the final state divided by the initial state. Right? So now if you just move delta G standard to one side and etc., you get this equation, right? So we're not really worried about delta G when it comes to binding. It's not a thing that we're going to use. We're more interested in the proportion of the complex compared to the amount of unbound molecules left over. During and prior to equilibrium, two processes are occurring at the same time. Binding, A plus B goes to AB with a rate constant K on, and unbinding AB to A plus B with a rate constant K off. Therefore, the rate for binding is rate on equals to K on times the concentration of A times B, and the rate of unbinding is rate off equals to K off times the concentration of AB complex. following the same type of math that we have done before for chemical reactions. At equilibrium, R on will equal to R off, which leads to the concentration of the complex over the concentration of A times the concentration of B, and that will equal to K on over K off, which equals to the Ka. It's the same math we did prior for chemical reactions, except we were doing K forward over K reverse. So note the following. As the concentration of AB increases, so does R off until equilibrium is reached. Even if the binding is weak between A and B, if A and B are at high enough concentrations, binding will occur. And neither one of these statements is anything different than what we said for chemical reactions. They're still true for binding reactions too. If you have an unfavorable chemical reaction, for example, let's say with an equilibrium constant of 1 over 100, well, if I have enough reactant, I'm going to get a little bit of product. So even if binding is not preferred, if I have high enough number of the molecules in a solution, a small proportion will be binding to each other. That's all this one is saying right here. And this one, well, of course, if I had a bunch of complex and the reaction was away from equilibrium and it required to go back to A plus B, then the R off would be favored, meaning the reverse process would be favored of unbinding from each other. And that's all that one is saying. Binding is not static. The delta G standard is giving information on the concentration of AB at a given time, but each AB complex is dissociating and reforming at a rate that is based on K on and K off. So what this is saying is that in a solution, if I have a bunch of A and B, and I have some more A and B, I'm drawing it in a different color, writing it in a different color for a reason, not because they're different from each other. And A, B, well, in one instant, for example, when I allow this thing to reach equilibrium, I could have, for example, A with red B, purple A, with green B, red A, with purple B, and let's say the rest are non-associated with each other. But in a different instant, like a millisecond or so later, depending on the K on and K off, this can change. Where now I have purple A with red B, and now I have green A, which I didn't have before because it was unassociated, with purple B, and I have black A with black B, for example. And then that could change again too. So just because two things bind to each other, and that's the preferred state, doesn't mean those two molecules are stuck together forever. Because of random thermal motion, they will come apart, they will reform, they will come apart, they will reform, etc. It's not a static binding event. And that's because it is reversible binding, right? And a part of reversible binding is that things will come apart and they will come back together. If the preferred state is that they come together at any one time, if I take a snapshot and I stop time and I just look at the numbers, I will have more of the complex than I will have of the unattached to each other, and that ratio will equal to the equilibrium constant for association. And that's all that we're saying. Now, the rate by which things come apart and they reform is based on these things, right? The rate on and the rate off. And that's going to be directly tied to the rate constants K on and K off and the concentrations of the different forms. The Ka and the delta G standard gives information of the strength of binding. So we've talked about this. We've said this. This is strong binding. These two things bind to each other strongly. But we never define what that means, right? The strength of binding is simply, at equilibrium, how much of each thing will I have? Will I have more of the complex or more of the molecules not complex together? If the ratio favors having more of the complex, then that is strong binding. Now compared to another two molecules that bind to each other, if their association constant is even bigger, then that means the strength of binding for them is larger. Let me use an example that I'm not using here because I'm using A and B. Let's say X plus Y goes to XY, and this is a Ka, and we have X plus Z goes to XZ, and this is a Ka, we'll call it Ka prime because they're different. If Ka prime is larger than Ka, then X binds Z with greater strength than it binds Y. So the strength of binding, that's what it means. We've never defined it before, and now we have. The K on and K off gives information on how quickly binding will occur, and we talked about that before. Example, Ka equals to 100 for A plus B goes to AB, right here. And Ka equals to 100 for A plus C going to AC. So the strength of binding is the same between them, but A plus B goes to AB, the K on equals to 1000, and the K off equals to 100, while for A plus C going to AC, the K on equals to 1, and the K off equals to 0.01, right here. And both of these things are fine as the equilibrium constant goes. If I use the equation K equals to K on over K off, well, for this one, I have K equals to 1000 over 10, which equals to 100. So we're good there because our equilibrium constant, our Ka, is 100 for both, right? So for the second one, right here, using these numbers, K equals to 1 over 0.01, which is also 100. So we're good with those. Therefore, the AB complex will form faster than the AC complex, even though the binding strengths are the same based on the Ka. The reciprocal of Ka is the Kd, or the dissociation constant. So Kd equals to 1 over Ka. Even a small change to the primary structure of a protein that leads to changes in the binding pocket can lead to big changes in the Ka. So consider 1000 molecules of A and 1000 molecules of B in a eukaryotic cell. The concentration of both will be about 10 to the minus 9 millimolarity. If the equilibrium constant K for A plus B going to AB is 10 to the 10, then one can calculate that at equilibrium there will be 270 A, 270 B, and 730 AB molecules. If the equilibrium constant is a little bit weaker at 10 to the 8, which is 2 logs lower than 10 to the 10, which represents a loss of 11.9 kilojoules per mole of binding energy from the example above, or 2 or 3 fewer hydrogen bonds, then there will be 915A, 915B, and 85AB molecules. Now some of you might be looking at this and going, wait, 10 to the 10 is a big number, right? How do I get here? I should have almost everything be AB, right? And 10 to the 8 is a big number. How do I get to this? And that is a really good question. And we're going to look at it and see how the math works out. So here's our setup. We have A plus B going to AB, and we have two different Kas, right? 10 to the 10 and 10 to the minus 8 from the example. Now we're going to say the concentration of A equals the concentration of B at 10 to the minus 9 molarity at equilibrium. Okay? And we want to calculate how much AB will have, the complex. Now we're going to do them side by side. Before I go on, I just want to put in the right units for the equilibrium constant. It's something that we didn't talk about earlier. So if you look at this, if my Ka equals to concentration of AB over A times B, then what I have is, I'm just going to stick in the units now, molarity over molarity times molarity, which equals to 1 over molarity, or molarity minus 1, right? So what we're going to do is we're going to stick in the units for these two, okay? And we're going to erase this. Okay, so moving on. Now we're going to do the left side, Ka equals 10 to the 10 in red, and then we'll do the left side in blue just so that the math doesn't get mixed up. So Ka equals to, and this is our central equation, so I don't have to write it twice. Ka equals to concentration of AB over concentration of A times concentration of B. And I'm going to plug in the numbers now. On the left, Ka is 10 to the 10, molarity minus 1, and we have AB, and that's what we're trying to figure out, times 10 to the minus 9, and this is going to be molarity squared because both of these things have the units of molarity. Molarity times molarity will be molarity squared. Now this part right here will become 10 to the minus 18, so I'm going to multiply both sides by 10 to the minus 18 molarity squared. So I have 10 to the 10 molarity minus 1 times 10 to the minus 18 molarity squared equals the concentration of AB, and that gives me 10 to the minus 8 molarity, because molarity squared times molarity minus 1 will give me molarity concentration of AB. Now 10 to the minus 8 molarity is 10 times higher as a number than 10 to the minus 9. You're going to have 10 times as much AB as you're going to have A or B by themselves. Now let's go ahead and look at 10 to the 8. Again, I'm going to plug in the numbers. We have 10 to the 8 molarity minus 1 equals to AB over 10 to the minus 9 times 10 to the minus 9 molarity squared. And again, doing the same math, this will be 10 to the minus 18 molarity squared. Multiply both sides by 10 to the minus 18 molarity squared, I get. And 10 to the 8 times 10 to the minus 18 gives me 10 to the 10 molarity, or 10 to the minus 10 AB. And 10 to the minus 10 is 10 times less than 10 to the minus 9, so I'll have 10 times less of the complex compared to the concentration of either A or B by themselves. And that sort of highlights the difference between the equilibrium constants for these binding reactions compared to the chemical reactions, because when we're doing the chemical reactions, we're simply looking at reactions that we had one reactant and one product. And those were the concentrations you were plugging into the equilibrium constant. If the equilibrium constant is greater than 1, it's a favorable chemical reaction, right? In this case, because the denominator right here is two concentrations, it makes the math a little bit different. And that's why 10 to the 8 is actually not that favorable. It actually favors the unbound state compared to 10 to the 10. Just showing you guys where that math came from so you don't get confused and when comparing the chemical reactions and their equilibrium constants compared to what's happening here. A few last notes. It is common for the concentration of one binding partner to be kept at a constant and for the concentration of the other binding partner to fluctuate. Example, enzymes and their substrates. We have gone over cellular respiration and glycolysis. The concentration of hexokinase and all those other enzymes that are in that glycolysis pathway, they're going to be pretty constant in the cell. What changes is a substrate. An enzyme plus substrate binding reaction has a Ka. That equals to this. So if E doesn't change, then if the concentration of substrate goes up, let's say I increase the concentration of substrate times 2. So substrate times 2. Remember, the Ka is an equilibrium constant. It cannot change. So Ka will equal to times 2. Well, I have a problem because I multiplied the substrate by 2. That means my Ka has changed? No, that cannot happen. So if I'm going to multiply the bottom by 2, I have to multiply the top by 2. So if one partner is kept at a constant and the other partner's concentration changes, the number of complexes have to change too to maintain the equilibrium constant, that ratio. And in the case of the enzyme, if you have so much substrate that the enzyme substrate complex is larger than the number of active sites available, then all enzymes will have a substrate attached to them. This is actually a very important concept right here. This right here, this is the only reason why I'm covering this. Because a lot of the stuff that we're going to be talking about later, it becomes much easier to understand if you just understand this relationship of binding. Where if one thing is kept constant but the other thing changes, then the amount of the complex changes too by the same amount. Now, if I was going to talk about a receptor ligand, so let's actually look at that. So let's say that on my cell surface, I have some receptor, and here it is. I have a whole bunch of them. It's the same receptor, okay? And here is its ligand. So the receptor plus ligand goes to receptor ligand has a Ka. And that Ka would be receptor ligand concentration, meaning the bound state like this, receptor concentration times ligand concentration. Now, if the amount of ligand is increased by 10 folds, we have ligand concentration times 10, then what will happen is, well, Ka would equal to receptor ligand, receptor times ligand times 10, which means that I have to multiply receptor ligand by 10 to maintain the equilibrium constant, the K of association. So if I increase the amount of ligand by 10-fold, then I have to increase the receptor ligand by 10-fold. That means 10 times as many complexes will be formed, and 10 times as many receptors are actually have the ligand bound. And that's why at low concentrations, hormone receptors are not binding the hormone as much, but at higher concentrations of the hormone, now the receptor ligands are forming, meaning the receptor is binding the hormone, and that leads to some sort of biological response by the cell. Very important concept. We're going to use this concept to explain a lot of things, and a lot of biology can be explained just by this right here. A direct example that we encountered earlier is pKa binding cyclic AMP to become activated. The concentration of pKa is relatively constant in the cell, while the concentration of cyclic AMP fluctuates. And this is something that we're going to look at in section 3, but all this is again saying is that if pKa becomes active when cyclic AMP binds to the regulatory subunits, if cyclic AMP concentrations are down, then not many of those regulatory subunits are binding cyclic AMP, so pKa is inactive, but when cyclic AMP's concentrations go up, so does the complex of cyclic AMP with the regulatory subunits, and thus you're going to start activating pKa. Same concept as before. It is common, depending on conditions, for binding strengths to dramatically change. For example, A plus B goes to AB is actually very unfavorable, meaning that this actually favors A plus B, not AB. Whereas A plus ATP gives me a phosphorylated ADP, and now A phosphorylated plus B will bind to each other with a delta G standard that is negative, so meaning that this state is favored. Remember the SH2 domain that we talked about previously? Imagine that B has an SH2 domain. Well, B cannot bind to A because A has not been phosphorylated at its tyrosine. So once A is phosphorylated at its tyrosine, now the B protein through its SH2 domain can bind to A phosphorylated. Okay guys, we're gonna stop here and then discuss enzyme kinetics next. Thank you.